Good afternoon, my name is Ben, and today I'm going to be talking about ASTM E8 or E8M, the standardized testing method for tension testing of metallic materials. The purpose of this test is to establish the testing method used to evaluate the tensile properties of metallic materials. Given a metallic material, this standard provides a procedure in order to evaluate the strength, ductility, and other material properties in response to uniaxial tension. The measured outcomes of this test include the applied load on the material, the specimen's initial and final geometry. The calculated outcomes include the stress and strain, and from this calculated curve, we may be able to determine the elastic modulus, yield strength, ultimate tensile strength, percent elongation, and percent reduction in area. This standard allows for two test specifications geometries, those being a sheet and a plate. I chose to adapt the sheet specification into 30 millimeter by 30 millimeter strips of an aluminum can. The test setup itself from the standard shows a grip on either side of the length of the material, as shown by my fingers below, and a tension applied across in either direction. The standard itself allows for uniaxial tension along the length of the specimen. I will apply this uniaxial tension across the length of the specimen given two homemade grips made from a 1x4 material I found in my garage. I used a saw to cut out a dado for spline used in the construction of screen to a door. This will apply the force of the grips onto the specimen without changing any material properties of the specimen itself. I drilled two holes to then allow for the grips to be tightened around the specimen so that it won't fall out given this uniaxial tension. I have the top half of the apparatus hung from an I-beam in my basement using fishing wire rated for 20 pounds of force or 9 kilograms. Once again, this apparatus holds the test specimen shown here using the spline as I described previously. When I attach the bottom portion of the apparatus, I will be able to apply a load measurable in order to form a stress and strain curve from which I can determine the material properties. Okay, here's the completed setup of the apparatus with the specimen in between the two adjustable grips hanging from an I-beam in my basement. I will now make sure that the device itself is level, which it looks to be, in order to ensure uniaxial tension due to gravity and gravity only. I will now measure the distance in between the two grips using a calibrated to 5/100ths of a millimeter, using this distance in between the calipers. Now I will apply a load using a fishing weight attached to a fishing wire to the bottom half of the apparatus. And I will be able to measure the deformation, once again using the same calipers, measuring the same distance here. After the load has been applied, I will measure the difference in the cross-sectional area this way, using the calipers once again. After completing this process for different applied loads, I am able to create a stress-strain curve from the engineering definitions of stress and strain using the differences in the applied load and the differences in the deformation. From this stress-strain graph, I am able to calculate the elastic modulus from the linearly elastic region of the graph, as well as the yield strength and the ultimate tensile strength of the material. Additionally, Using the reduction in the cross-sectional area and the elongation of the material, I should be able to calculate the percent elongation and the percent area reduction of the aluminum given different applied loads. Some limitations of my apparatus include the clamps themselves, which may not be as precise as the standard calls them to be. Spline may not hold a consistent grip on either side of the specimen and cannot be tightened to a specific force due to limitations from the nut bolt system. Additionally, these clamps may degrade on the aluminum, decreasing the accuracy of the calculated mechanical properties, as well as the strength of the overall apparatus. Additionally, since loads are calculated manually, there's room for human error, as well as the fishing weights themselves being used, which may leave room for wear and tear on the materials, leading them not all to have the same mass. Since length calculations and load calculations are made manually and not continuously through the standard apparatus specifications, there will not be as many data points on my final stress strain curve, leading to potential inaccuracies when measuring the material's properties. Additionally, the specimen may not be completely loaded in uniaxial tension due to inaccuracies when aligning the specimen up with the grip apparatus, which can lead to, once again, inaccuracies in the final results.